Okay, let's get started. Today, we're going to talk about spectroscopy and spectrometry. I listed a number of sources. There are more, but these are excellent sources. Big ones are number 3. I highly recommend the Silverstein book. The SDBS website that has a number of different compounds with a lot of different spectra. You'll find that I used them as a resource for your examples quite a bit. And also, the website from UCLA, they give you a ton of problem sets to do. And it's really important that you practice. So spectroscopy is an analytical technique, which means that all we're doing is we use spectroscopy to determine what we have in our sample. And oftentimes it uses very little amounts of sample, and it destroys very little or no sample at all, which is very nice because sometimes when we do syntheses, we don't really form that much final product. To be able to recover it after we do our analyses is important. When we talk about spectroscopy, we're actually using different areas of the electromagnetic radiation spectrum, and it gives us different types of information. So the types of spectroscopy that we're going to be focusing on would be IR, or infrared spectroscopy, that measures bond vibration frequencies. Okay, and we'll spend a lot of time talking about how we use IR to determine the presence or absence of functional groups. We will also be talking about nuclear magnetic resonance, NMR. We'll focus on protons and on carbon-13, although there are a number of other nuclei that you can use, like N15. We use it to determine molecular structure. We can also use it for kinetics and equilibrium studies. This is especially if the reactions, the equilibrium studies, occur at the same time scale as NMR. We also talk about ultraviolet, UV-Vis, actually spectroscopy, and is used to examine electronic transitions to determine bonding patterns. And usually it's used for pi bonds and conjugated pi bonds. What about mass spectrometry? Mass spectrometry, we measure the mass to charge ratio of ions, and we plot the intensity versus the mass to charge ratio. Most of the time when we talk about a molecular ion, the charge is a plus for the molar mass. Now, mass spectrometry is a very, very powerful tool. We can get the molar masses in high resolution of unknown compounds, as well as just getting the molar mass of unknown compounds. If we do fragmentation studies, we can start determining structure, so we have an understanding of the functional groups that are present. When we look at specific elements, we can look at their natural abundance with an isotope, so that's proven to be very useful. And with a high resolution, high precision, we can look at the natural abundances of isotopes, so that's how we can calculate what occurs naturally and get our atomic weight for the periodic table. With the molar masses, because it's high resolution, we can actually distinguish between several different types of molecular formulas and know which one we're looking at. Also, it has no size limitations. So when you look at mass spectrometry, we can be looking at elements. We can look at small organic compounds, and that's what we'll be focusing on. But you can look at larger peptides and proteins, and sometimes we look at mixtures that are from cells. Okay, it has high sensitivity. We'll have femtomolar type concentrations, or we're looking at nanograms to picogram amount of material. Unfortunately, though, the sample is destroyed in the ionization process, so we don't recover our material. Okay, so here's the electromagnetic radiation spectrum. High energy, gamma rays, these can break bonds. Remember, this is ionizing radiation. X-rays, we know what we use X-rays for. We can use X-rays to determine structures by doing X-ray crystallography. but we won't be talking too much about X-ray crystallography in this course. Okay, ultraviolet radiation, so it's the UV vis in that region right there that we'll be looking at electronic transitions. Infrared radiation on the red side of visible light, that's what we're going to start with first, and that talks about vibrational modes. Microwaves are rotational modes, and then radio waves when we talk about nuclear spin. So again, here's a summary. When we look at gamma rays, X-rays, and the vacuum UV, these are ionization effects. When we look at near UV and visible, the UV vis, we're looking at electronic transitions. When we look at infrared, we're doing molecular vibrations. Microwave, we won't be talking about, but you do get rotational motion. And with the microwave, that's how microwaves work, because it does do rotational motion. We focus for a rotational motion of water. And then the radio waves, these are our nuclear spin transitions. All right, infrared. It's just below the red in the visible region. We saw that. Wavelengths are usually 2.5 to 25 micrometers. Our common units that we use for infrared are wave numbers, and those units are inverse centimeters. Now, inverse centimeter is equal to 10 to the 4th divided by my wavelength, which is in micrometers. Wave numbers are proportional to frequency and energy. Okay, they're not the same, so you do have to convert, but they are proportional. That means if I have a larger value for a wave number, it's a higher energy vibration, higher frequency vibration. Okay, so let's talk about some of the vibrations. So the first set of vibrations we're going to talk about are stretching frequencies. So when we're talking about stretching, it's kind of like, instead of that wooden stick when we do ball and stick models to build our molecule, instead think of this as a spring and two balls on it. So if our bond is like two balls on a spring, you can stretch it, you can compress it, and it goes back and forth. And that equilibrium is what we talk about for the bond length for that particular bond between the two atoms. Now what we can do is, because we do this, we can approximate using Hooke's law for springs. Okay? So what is Hooke's law? So the way it's written is the wave number is equal to 1 over 2 pi c, where c is the speed of light, but the units are going to be in centimeters per second. Okay? That's K is our force constant for the bond. It's dynes per centimeter. And not surprisingly, it's stronger for double bonds and even stronger for triple bonds. If we say it's about 5 times 10 to the 5th dynes per centimeter for single bonds, then it's about double that value for double bonds and triple that value for triple bonds. Okay. The m times m1, m1 times m2 divided by m1 plus m2 is mu, the reduced mass. So this, if we simplify it, it's going to be the square root of k divided by mu. And the mass of the atoms of M1 and M2 must be in grams. So you're looking at the mass of an individual atom. So let's give an example. Okay? So a CH stretch. So a carbon atom is about 1.99 times 10 to the minus 23rd grams. A hydrogen atom is about 1.67 times 10 to the minus 24th grams. Okay? And then K, for a single bond, we said was about 5 times 10 to the 5th. And C, the speed of light, because it's centimeters per second, it's going to be 3 times 10 to the 10th centimeters per second. Okay? So, if you look at your reduced mass, if you look at your reduced mass, M1 times M2 divided by M1 plus M2, we get about 1.54 times 10 to the minus 24 grams. Okay, so if we just plug in our numbers into our formula, then we get our frequency for CH stretching is about 3025 wave numbers. Now the real range for an sp3 carbon hydrogen stretch is 2960 to 2850 wave numbers. Okay, so why the difference? Because don't forget, we're ignoring the environment around the CH. So this is really quite a good approximation. Okay, so let's go through the bond stretching frequencies. Okay, so as you can see, as I increase the mass of my atoms, I decrease my wave numbers. Okay, so think about, if you just think about doing paddle ball, you have a light ping pong ball on your paddle ball paddle, then you can actually have a high frequency. It doesn't take that much. If I do something like put a golf ball on there, it's much heavier. It's harder to get that high frequency. Okay, so my frequency decreases. If I did paddle ball with a tennis ball, same setup except it's a tennis ball, now my frequency is definitely going to decrease. What about the bond energy? Well, we were just talking, if this is a weaker bond, at least it's 1200. With a stronger bond, it's going to have a higher frequency, 1660. And with the triple bond, it's around 2200, just below 2200. Okay, so it decreases with increasing atomic mass, and it increases with increasing bond energy. Okay, so what are some of these vibrational modes? So if it is a nonlinear molecule, then the number of vibrational modes is going to be 3n minus 6. Okay, where n is the number of atoms, and that's approximation. Linear molecules, okay, with n atoms is typically around 3n minus 5. Okay, so what you're going to see in your IR isn't just symmetric stretching, anti-symmetric stretching. So we have just some random coordinate to try to determine where my symmetry and anti-symmetry is. But we have scissoring, okay, as well, where my hydrogen atoms are just going to go like that. Okay. Here, here's my, where do they fall? So, for water, it falls at, okay, symmetrical stretching, 3652, 3756 for asymmetrical, okay. For carbon dioxide, which we typically don't see in IR because we subtract it out, okay, because it's in our background, but you'll see your scissoring, your bending here. You'll see your asymmetrical stretching. You'll see your symmetrical stretching at 3340, at 1340, sorry, 2350, 665, 665. The more interesting one is down here. So we're looking at a methylene unit, a CH2 unit, where I have an attachment to another atom here and here. Let's say carbon atoms. So what's happening with my CH stretches? So when I have symmetrical stretching, that occurs at 2853. When I see the asymmetrical stretching is around 2926. So remember, we were talking about the range from 2960 down to 2800 or so. You're going to see this quite a bit. The in-plane bending, or that scissoring, that's at 1465. So when you start getting in the 1400s and lower in terms of our wave numbers, we start migrating over into what we call the fingerprint region. And the reason we call it the fingerprint region is you're going to have a lot of absorbances there. So if we have sp3, right, carbon-hydrogen stretches, you'll typically see a 1465 scissoring stretch, an in-plane bending. What's interesting here is the out-of-plane bending called wagging and twisting. So wagging, if this is my carbon right here, then wagging is their hydrogens are both going out the plane and in the plane. Twisting is kind of like you're exercising, you're twisting this way. And then the in-plane bending or rocking, you're just rocking. And that's at 720. Okay, and that can be fairly distinct. So the fingerprint of a molecule. So oftentimes what we'll do is that stretching is in this range, and then here from 1400 to 1600 we'll see some stretching, becomes more complex, And then we get complex vibrations from 600 to 1400, or the fingerprint region. Okay, now no two molecules give exactly the same IR. So what you can do is, if you have an unknown substance and you have a reference compound, you can take the IR of both and then overlay the two. And basically, if your substance, your unknown, is exactly the same as your reference, you will have exactly the same IR. Okay? IR active. So it turns out when you look at IR, we can't see every single vibrational mode in IR. So what do we need besides these vibrational modes? Okay, you need a polar bond. You have to have a permanent dipole. If you have a polarizable bond, like carbon-hydrogen, it's only 0.4 if you look at electronegativity. That's still polar enough for you to see it. Okay, and you need to be able to have something polarizable, so you have to have some electron density. If it's a nonpolar bond and it's very symmetrical, you may not be able to see it at all. And you're going to have to use Raman spectroscopy or other types of spectroscopies to identify what you have. So what we're really looking for is a change in our dipole moment as my bond is compressed and stretched. All right. Let's look at different types of spectrometers. Okay, so originally what you would have for an IR is you'd have your source. Okay, it's got to be a heat source because we're talking about IR. And the beam would be split, and one would go through your sample cell, and one would go through your reference cell, which is basically just open to air because that's your reference. Okay, and it would be recombined. And then when you look at it, okay, what you would see is this is a percent light transmitted. So here, some of the, not a lot of light got absorbed. But over here, as I look at this wave number, this is a higher value, it absorbed a lot. So you're looking at the difference between what it should be just through the air and what happened when you, what frequency was absorbed when you went through the sample cell. This is how it was. It's fairly simple, but we have to make sure that we have the path length exactly the same. But here's the thing, you need a lot of sample, and you need to scan through all your frequencies. What that means is it's slow. Okay. So now what we do is FTIR, the Fourier transform IR. Now we use interferometry. So basically it's an interferometer that we now have. It has a much better sensitivity. Scans are 1 to 2 seconds. So if you have very little material, you need to average them out. You can take, in a minute, think about how many scans you can do if they're 1 second. 60 scans and average them. Okay. The amount of energy you need is much less. Okay. And you use a laser beam to keep the instrument calibrated. So you have very, very high precision. These two sources are excellent in understanding the basics behind interferometry, FTIR. So if you're interested in reading more about it, I highly recommend these two. All right, so let's go through. Here's my helium neon laser. And all I'm interested in this is that it's going to have a certain frequency. And with that frequency, that's what's used to tack on and drive the movement of my mirror. Okay? So this is essentially a Michelson-Morley experiment. What happens is you've got your source, goes through a beam splitter. Okay? So half of your beam goes to your fixed mirror, half the beam goes to your moving mirror. And then when it bounces back, it recombines, and you have your sample, goes through, and then it detects it. Okay? Now, why do that? All right? So when I move my mirror, I'm out of phase. So when I combine, I don't have basically very much of a combination. It's like destructive interference. But as I continue to move my mirror, I get constructive interference, and then I continue to move it away, get destructive interference. So, if my x-axis is basically time, which is linked to the movement of my mirror, okay, then as I'm linking it to the frequency of my helium neon laser, I move my mirror, and I'm out of phase, and I slowly go in phase, I go out of phase again. And this is called an interferogram. And what we have to do is convert it from my time to how many frequencies are in here. Okay, so let's take a look. Here's an example. If I have two waves that are really close together, okay, then when they add together, they're going to form what we call a beat, this envelope. Okay, so when you measure the distance between your two envelopes from your beat, okay, that is 1 over D, where D are your two frequencies. So if you've ever tried to tune a guitar, and you have your tuner and you've got that note going, and your guitar string is very close to it, but not quite the same frequency, then you'll hear that wah, 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 wah. And those are the beats that you're hearing because they're very close together and they're doing constructive and destructive interference. Why is that important? So from here, when you do your Fourier transform, you can convert your time into what are the frequencies that compose this beat. So now let's take a look at your interferogram. You've gone through and you've measured your interferogram. If you multiply this part by 100, you can see now that I'm getting beats here because of all the frequencies that are combining in there, both constructively and destructively. So when we do a Fourier transform from the time so we can get all the frequencies, what we're asking really is, what are all the frequencies that exist in here that would produce this type of constructive and destructive interference wave? Kitty. Okay, before our interruption by Blosky. So basically, when you do the Fourier transform, what you're interested in finding is what are all the frequencies associated with producing a beat, this type of interferogram, okay? And so when you do that, that's how you get all your absorbances, okay? Now, this is what happens. When I run my FTIR on my sample, this is what the interferogram looks like. When I do the Fourier transform, then basically these are all the different frequencies that cause this pattern. Okay, and we're looking at the beat pattern really towards the tail. Now, remember how we talked about the CH stretch and SP3 CH stretch? Oh, look at that. 25, 6, 7, 8, 3,000, so it's between 2,800 and 3,000 wave numbers. These are all SP3 CH stretches. Scissoring, remember we were talking about the 1465 scissoring? Look at that, right there. And then remember we were looking at the 1365 for basically the wagging and the twisting. Weren't we saying it's right here? And wasn't the rocking right here around 700? So this octane, basically you can just see how gorgeous this is. Now the fingerprint region runs from here to here. This is a little messy, starts getting cleaner up here again. Okay, see some overlap. But this is a fingerprint region. This is very clean for a fingerprint region. Sometimes it's going to look very, very complex. Don't expect to be able to assign every single peak like we have here. Okay. So the Fourier transform again converts from the time domain to the frequency domain. Okay. Carbon-carbon bonds. Carbon-carbon single bond at 1200 wave numbers. Very difficult to see. Okay, I'm going to go back. 1200, right? Why don't we see it? Because it's nonpolar. If you really needed to see the carbon-carbon stretches, you're going to be looking at Raman spectroscopy. Carbon double bond carbon, this is more polarizable, so you actually do see that this is about medium, around 1660. Okay? If you see variations of that, like we talked about here, any variation will give you an idea of what's happening. Isolated, 1640 to 1680. If it's conjugated, look, it lowers the frequency. Aromatic lowers the frequency. Okay? A triple bond, just under 2200. Okay? If it's internal, it's weak or absent. But if it's a terminal alkyne, or it's at the very end, I have a hydrogen on one side, because of the asymmetry of it, you're going to see it. It'll be weak to medium. Okay, carbon-hydrogen bond stretching. sp3, the more S character, it absorbs at a higher frequency. Oh, no, they're 3300, I'm so sorry. sp3ch, just below 3000. sp2ch, just above 3000. spch, 3300. And if you see this, and you think you have a terminal alkyne, you're going to look at just below 2200 for the carbon triple bond carbon stretch. Okay, so here's essentially a summary. Your NH stretches, your OH stretches, this is NH and OH, they tend to be broad. This one is a nice round broad one. This is broad but ends in a peak, a single peak if I have one hydrogen, two peaks if I have two hydrogens on the nitrogen. Carbon triple bond carbon, just under 2200. Carbon triple bond nitrogen, this is polar, so it's going to be medium to strong, just above the 2200. Carbon double bond carbon, we already said, was around 1660. Carbon double bond oxygen for a ketone would run around 1710, 1715. Carbon double bond nitrogen around that same region. Okay, so this tends to be medium. This is very strong, beautiful. One of the things that IR carbonyl stands out just beautifully. Carbon double bonded nitrogen, you'll see that pretty well as well. Carbon-carbon, hardly see it all. That should have been around 1200. Carbon-oxygen, depending upon what you're looking at. If you're looking at carbon-oxygen like it's in an alcohol, okay, or it's and you can tell the difference between if it's a tertiary, secondary, or primary carbon, it'll be between about 1000 and 1100 here. Carbon-nitrogen, the same. If this is carbon-oxygen for your ethers, it's also around here, or you'll see it slightly higher, closer to 1200 if you're looking at an sp2 carbon-oxygen. So don't forget the effects of hybridization. In the 600 to 800 region, you're going to see stretching frequencies if it's carbon to your halogens. So around 1000 carbon fluorine. If you see closer to carbon chlorine, it's closer to 800. Carbon bromine is closer to between 700 and 800. Carbon iodine, closer to 600 to 700, if not slightly lower. Okay, this is a fingerprint region because in this region we'll also see out of plane bending for aromatics. Okay, so let's do a little longer here. Carbon fluorine, 1000 to 1400. Strong. These are all strong because of their polar bonds. Carbon chlorine, 600 to 800 in the fingerprint region. Carbon bromine, 500 to 600, and carbon iodine as well, around 500. Okay, so let's take a look. Okay, so here, if I'm assigning it, look at this. This is just below 3000. So that tells me I have sp3 carbon hydrogen stretches. Okay, if I look at this one, remember we were saying around 1465 or so was my carbon hydrogen. Okay, this is fairly strong, but this should be my carbon hydrogen. Now some of these may be associated with the bromine, but let's take a look at the bromine. Remember we were talking about the bromine stretches? And that was strong, and a carbon bromine stretch was around 600. So let's take a look. Let me go back to that table. Here we are, 500 to 600. That's between 500 and 600. This is my carbon-bromine stretch. Okay, these are strong, but not necessarily easy to identify. All right, let's take a look at some of the fingerprint regions. Now, the reason I want you to also look at the fingerprint region isn't because I thought, oh, listen, I have all this fun stuff for you to do. It gives you a lot of information, okay? So don't neglect it, but don't rely only on it. When you look at the fingerprint region, we know what the carbon-carbon double bonded was, but these are your out-of-plane carbon-hydrogen stretches, okay? So when you do that, look at if it's monosubstituted, you have two strong peaks between 900 and 1,000, okay? If it's cis, look at, you only get one type of strong stretch here. Trans is higher, almost 1,000, whereas the cis is closer to 700, okay? Your 1,1 disubstituted, you can look at the types of substitutions. And why don't I see anything for tetrasubstituted? Because we're looking at carbon-hydrogen stretches, and there are no carbon-hydrogen stretches there. Okay? What about aromatic out-of-plane bending? I apologize, this is a little on the blurry side, so we'll go through this. If it's monosubstituted, in the fingerprint region, I see two strong peaks. If it's ortho, I see a single one around 750. If it's meta, look at, I have three of them. Okay? Para, I only have a single one. Now the difference, 750, 800. Okay? Are there other types of spectroscopy to help us identify the type of out-of-plane bending? The answer is yes. Okay? But what's nice is that once we accumulate all our data, we can see how things confirm each other. And that's the key to the fingerprint region. 1, 2, 4 substitutions, these two, 1, 2, 3, lower frequency, and 1, 3, 5, look at the greater separation. Okay, so you can use your out-of-plane CH stretches on aromatics and on alkenes to help to determine the type of substitutions you have. Okay, so let's go through a couple of spectra and then we'll move on. Okay, this is just below 3,000, so you know it's SP3 CH stretches. Remember we said around 1465, that was the CH scissoring. Between around the 1300s, 1350, 1360, we have, this is CH bending. It's actually your wagging and twisting. And remember around the 700, we're going to see our rocking, CH rocking. Okay, now look at here again, just below 3,000, SP3 CH stretch. But I also have something at 3080. That's my SP2 CH stretch. So now I'm thinking, oh, I have a double bond somewhere. So let's take a look. All right. That's hard to distinguish. We may be getting harmonics. But look at this, 1642. And the range was, we were thinking 1660, but the range was 1640 to 1680. 1642. That is a beautiful carbon-carbon double bond. This is my CH scissoring. This is my CH twisting and rocking. What are these guys? They're not assigned because we're not sure, right? Maybe it's a carbon-carbon stretch, but that's around 1,200. So we're not going to assign it just because the bottom line is that if you're not sure, you can leave it blank, especially on IR, because you can get lots of peaks. Some are overtones, and there are just so many different types of vibrational modes. Okay, so we're going to pick out the ones that we do know to try to piece together what we're looking at. So we may not be able from this IR, and don't expect that you'll be able to say, oh, it's one hexene. But what you can discern from an IR is I have alkyl groups, and I have a carbon double bond carbon, and I have a carbon CH stretch. And that's an sp2 carbon. So, can you tell me I've only got 6 carbons, if not 8? No, this does not tell you that. Okay? All right, alkyne. Let's compare a couple of alkynes. Okay? So in this one, I have all these sp3CH stretches. Okay, so I have a bunch of alkyl groups. But look at the 3300. Isn't that gorgeous? This 3313 peak is an SPC carbon hydrogen stretch right there. So if I think I have a terminal alkyne, then I should be able to see just below the 2200 at 2119 my carbon triple bond carbon stretch. So you know you have a carbon triple bond carbon at the very end of my chain, and everything else are alkyl groups. Okay, CH3s, CH2s. Okay, again, isn't that my scissoring? Okay, and then this is 700, not sure. Okay, now what about this one? We don't see a carbon triple bond carbon. We don't see a carbon triple bond carbon hydrogen stretch because it's not terminal. All we know in this IR is I have alkyl groups. That's it. And what we'd have to do is we'd have to look at our other information in order to get our structure. Okay, let's take a break right now. Okay, let's move on. All right, let's take a look at an aromatic spectrum. You can see that above the 3000 mark, I have peaks that are representative of sp2 carbon hydrogen stretches. And below the 3000 mark, I have a few peaks that are representative of sp3 carbon hydrogen stretches. So we know I have alkyl groups and sp2 carbon hydrogen groups. Then we take a look and we say, oh, look at around 1600, I see a carbon double bond carbon stretch. Well, we know that an isolated carbon double bond carbon should appear between 1640 and 1680. Why is it down in 1600? So it has to have been conjugated. So now I'm thinking, okay, I have a conjugated system. Then let's take a look at the aromatic region. This is the fingerprint region. 700, 750. Remember, we were talking about those strong out of plane CH bends that occur, okay, at the fingerprint region. And when it occurs between 700 and 750, that tells me I have a monosubstituted aromatic. So with this 1600, thinking it's conjugated and the aromatic fingerprint, okay, I'm thinking, okay, so we know we have basically an aromatic that's monosubstituted. Okay, looks like I have some alkyl groups, so there's got to be some alkyl groups that's part of the substitution. How many? We don't know. In this case, it's toluene, I just have a methyl group. But the mere fact that we can tell this much on IR is important. Okay, so we were talking about OH and NH stretches. And with the OH stretches, you have a broad rounded tip. If I have NH, it's broad, and the sharp spikes have to do with whether I have one hydrogen, one sharp spike, or two hydrogens, two sharp spikes. If I have no hydrogens attached to the nitrogen, you won't see it because there's no NH stretches. Okay, so let's take a look at the alcohol. See, this is that nice broad peak. Okay, and this is occurring around 3300 or so. Okay, and I have alkyl groups. So from here I know I have alcohol, OH, and I know I have CH stretches from sp3. Okay, what's unreliable is my CO stretch. Okay, around, this is around 1030 or so. The only reason is you can see there's just so many absorbances here. It will be strong, okay, because of the polar bond, but there are a lot of other absorbances. So we need to bear that in mind. Okay, here, if I look, this is very broad. It's broadened down. See that? Broad, but a spike. So from this appearance, I know I have an NH, not an NH2, but an NH, because it's a single spike. Good. Then I have my CH stretches. Okay, that's just below 3,000. Okay, here, that's a CN stretch, but like we had mentioned earlier, with the CO stretch that we saw, unreliable because, okay, this region has a lot of absorbances there. Okay? Alright, carbonyl stretching, one of the most beautiful stretches, absorbances you'll ever see. Okay? For simple ketones, aldehydes, and carboxylic acids, it's around 1710 wave numbers. Once you know what the wave numbers should be, then what's nice is that if you see that there's a deviation from there, then you can start thinking about more aspects, the environment it's in. So instead of 1710, if I see higher wave numbers, I'm thinking there might be a strained system, or I could have a very strong electron withdrawing group. Okay, esters appear higher. Okay, cyclobutanone would be higher. Okay, acid anhydrides are higher. If they're lower, okay, then we're thinking conjugation. Okay, so amides, because of the resonance form on amides, will have a lower frequency than 1710. Because this is such a strong polar bond, it's one of the strongest signals on your IR. Okay, if you see that you have an OH stretch, you're thinking carboxylic acid, be aware when you see this hydroxyl group, we saw that 3,300 for the alcohol, it's much lower. It's going to be around 3,000. And it occurs right under that CH stretch. So it makes it very messy, but you can kind of see that. It's very, very, see how low that frequency is. So that'll give you an idea you have carboxylic acid. Okay, aldehydes. Aldehydes are really pretty. So you'll see your carbonyl stretch around 1710. And you'll have two CH stretches. These are based off of that sp2 carbon hydrogen bond. But they occur at 2,700, 2,800, around that range. And they run around medium or so. One is symmetrical, one's asymmetrical. What's pretty bad, it almost looks like vampire teeth. It's very distinctive. When you see that along with your carbonyl stretch, you're thinking, I have an aldehyde. And then you can look for other functional groups in your molecule. All right, so let's take a look at your ketone. Nothing above 3,000. Okay, below 3,000, I know I have alkyl groups, just sp3 carbon hydrogen stretches. 17, 18, what a beauty, right? That's a strong signal. That's your carbonyl stretch. Okay, so, and that's about our take-home message for this IR. Okay, now what about these guys? Okay, probably you're rocking, probably here, the 1465, you're scissoring, and then over here is probably you're twisting and wagging. But the bottom line is that now that you start getting the fingerprint region, it's a little harder to know. But this is a crystal clear absorbance for your carbonyl. And these guys are crystal clear. So anything above 1,600 is very, very clear. Listen, look at your aldehyde, alkyl groups, right? These are CH stretches. Look at that. Doesn't that look like vampire teeth just sticking out there? You have your carbonyl. This has got to be an aldehyde. Okay? So, this pattern is very indicative of an aldehyde. That's just beauty. Look at this. The reason that my frequency is lower than the 3,300 is because of all of this hydrogen bonding. Carboxylic acids are very good at hydrogen bonding. Because of that, it broadens it out and it also decreases my wave number. So now it's lower here. And you can see now what I'm saying. here's my OH, and it's right underneath my CH stretches. These are my CH stretches for my alkyl groups. And then I have this beautiful carbonyl stretch. So this combined with the OH, okay, tells me I have a carboxylic acid. If I see this carbonyl, but I see an OH, but it's way up here at 3300, then my suspicion would be maybe I have a hydroxyl group and I have a carbonyl group, but they're not forming a carboxylic acid. So just kind of be aware these changes in your frequency give you an indication of what your functional group is. Conjugation, we were talking about the conjugation of your carbonyl will lower your carbonyl frequencies, 1710 down to 1680. Okay, amides are very low. Esters are, because of the electron withdrawing group, are very high. Small rings, okay, because they're strained, very higher frequency. So let's take a look at both of them. Do you see this? This is broad in that region, but I have two spikes, so we know it's not an OH. We know this is an NH, and it's got two hydrogens to it. Beautiful, right? NH2, okay? Then I have alkyl groups everywhere. And then I go down here and look at this. 1630 to 1660, carbonyl stretch. That's so, so intensely beautiful. So from this low frequency, I'm not thinking I have a ketone and an amine. I'm thinking I have an amide. And it's a primary amide because I have an NH2. Okay? What about this guy? I don't see anything up here. Okay? Now it's acetic anhydride, so I have actually two methyl groups. So I should see something up here. Well, it's so small compared to everything else, you're not going to detect it. Okay? So you don't necessarily just conclude it's completely gone, I don't see anything, doesn't exist. Tells you that maybe it's just so little material there you can't see it. Okay? Now, I have two distinct separate carbonyl peaks. And look at this. One's at 1750. This one is at 1810. So I went up in terms of wave numbers, higher energy, up like, what, 100? Right? From 1710 to 1810, that's 100 wave numbers. That's pretty significant. So that's going to tell you, because of this shift to higher frequencies, higher wave numbers, that I'm in more of a strained system, or I have a very strong electron withdrawing group attached to this carbonyl. And sure enough, okay, you have that right there. Okay? Now what about this beautiful peak here? That's my CO. Okay, stretch. Now, is it reliable? Now that you know the structures, you know what? I suspect that's going to be a CO stretch because I think I have an anhydride, but we're going to have to confirm it. But these guys, you know, are carbonyls. Okay, what about this one? Okay, I have sp3 carbon hydrogen stretches. I have a gorgeous, gorgeous carbonyl group. That's at like basically almost 1800. So I know I have a very strained system or an electron withdrawing group. And sure enough, it's cyclobutanone. This is highly strained. Okay? And then here's probably my CH2 scissoring. Okay? That's occurring there. But like I say, over here you have so many absorbances, it's going to become harder. But that carbonyl is just like a spotlight, and so are my CH stretches there. Okay, so for carbon-oxygen, we were talking about them not being super reliable. They are there. So you can assign them, but just be careful when you do about relying on them only. Get additional information as well. For alcohols, okay, you have a range from 1,000 to about 1,200. Primary, secondary, and tertiary. So tertiary is going to be a higher frequency. When you look at ethers, okay, again, aliphatic ethers, Okay, but then when we start getting to sp2, that's my sp2 carbon oxygen. That's my sp3 carbon oxygen. Vinyl ethers, again, sp2 carbon oxygen, sp3 carbon oxygen. So you're going to see two peaks when you get your ethers. Okay, so let's take a look at this guy, ethyl acetate. All these are less than 3,000, so we know that's sp3 carbon hydrogen. 1742. Okay, just really, really pretty. A little bit higher frequency than 1710, so you think, that's interesting. Okay, then we have these peaks. Probably this is a carbon oxygen. Probably it's going to be my sp2 carbon oxygen, because we know that that's where around the 1200 mark is where carbon oxygen, if it's sp2 carbon. And then here is most likely your carbon, sp3 carbon to oxygen, because that's around 1,000, between 1,000 and 1,100. Okay? This guy is probably from your CH. Probably some of your, it's not the 1460, maybe your wagging and your twisting. Okay? So, carbon nitrogen absorbs around 1200. Carbon double bonded to nitrogen around 1660. It's going to be stronger because I have a stronger dipole. And then remember, your nitriles are going to be just above 2200. Alkynes just below 2200. Okay, so here's a nitrile. See, 2249 have just alkyl groups everywhere else. Okay. Carbon-carbon, not really observable. Around 1130, we were talking about carbon double bonded to carbon. Okay, so not as strong. Accumulated alkenes, these are very strained. Notice it moved up about 300 wave numbers. Conjugated moves to longer wave numbers. And then remember, alkynes, you're going to only see the terminal alkyne. If it's internal, you won't see the triple bond carbon stretch, but it's weak to medium, and it's just below the 2200. So let's take a look at this guy. See that? That's going to be what? 3023. And then I have the rest that's below 3000. This tells you have an sp2 carbon hydrogen stretch. So you have the structure, but let's say you don't have the structure. You're thinking, oh, I might have an aromatic, I might have an alkene. So let's take a look. See how weak this is? This is my carbon double bonded carbon stretch, right? Around 16, looks like 1640. Okay, so that's kind of typical. All right, and then this is most likely you're stretching and wagging. Okay, and then we have these two, not at 700, 750 for monosubstituted, but we see the fingerprint. So you could take a look and see whether or not it matches my alkene out of plane. But the bottom line is right now, it looks like we have an alkene, and it looks like we have sp3 carbon alkyl groups, because we have also sp3 carbon hydrogen stretches. Okay. What about the 1,4-cyclohexadiene? Again, CH, sp2, CH stretch, sp3, CH stretch. Look how much stronger this is, because I have two carbon double bonded carbon stretches. Not just one, but two. So they're going to absorb twice as much. Okay? Look at this. 1, 2, 3. That's a little over 3,300. Not broad. Nice and sharp. That's got to be a terminal alkyne SPCH stretch. Everything else is sp3 carbon CH stretch. And look at this. Isn't that pretty? That's at 2,000, about 2,100. It's below 2,200, right? So this is going to be my carbon triple bond carbon stretch. Okay? So far so good. And these guys will all be from your fingerprint region, your out of plane and in plane, symmetric and asymmetric type CH wagging. Okay? Look at this one. Again, I just see an alkyl group. I don't see my terminal alkyne CH stretch because there is no terminal alkyne. And then here, that looks more like noise. I don't see my carbon triple bond carbon because it's internal. So from my IR, it just looks like I have alkyl groups. I cannot detect an IR, an internal alkyne. Okay? Strengths and limitations to IR. So, you can't determine a structure. You can only determine the presence or absence of a functional group. Okay? And just be careful. The absence of a signal depends on the signal. If you don't see a carbonyl stretch, you do not have a carbonyl in your molecule. But some of the weaker ones where you don't want to rely upon absence of that, just take it with a grain of salt. Okay? If you see it, then that functional group is most likely there. Okay? So this is really important. So this is the one that you have to be careful with taking a grain of salt. Be aware that some of the signals, when we assign it, you want to make sure you know. Because when we get down to the fingerprint region, you can get some ambiguity. Correspondence with a known sample will confirm your identity. So if you have a reference and you compare the two, then you'll know what you have. Let's take a look at a couple examples for identifying functional groups. All right. What about this guy? Okay. I don't have anything above 3,000. So this is an sp3 carbon hydrogen bond stretch, which means I just have alkyl groups from here, but also notice here at around 1743, I actually have a carbonyl. So I have alkyl groups and a carbonyl, and around 1240, that's a really nice, beautiful, strong stretch. That is most likely a carbon-oxygen stretch. So if I had to combine this, and this is 1740, which is a little higher frequency than the 1710, I suspect I have an alkyl ester. So my functional group would be an ester. I have a carbonyl and an oxygen attached to that carbon, and I have alkyl groups on it. What those alkyl groups are, I don't know, but I suspect I have just an alkyl ester. No aromatics, no carbon, double bond carbon. Okay, what about this guy? Oh, okay, so above 3,000, I have some sp2CH peaks. Okay, below 3,000, I have some sp3CH stretches. Okay, and then that's noise or impurity. Oh, at 1690 or so, I have a carbonyl stretch. What this tells me, it's not a 1710. I suspect I have conjugation, because I see both the alkene type CH stretches, and I also see that my carbonyl is not a higher frequency, but my frequency was lower. And then you look and say at 1600, look at that. I have a bunch of carbon double bonded carbon. That's a carbon double bonded carbon stretch. It's fairly strong, so I should have a lot of them present, right? Okay, so this one right here, that's probably from my alkyl group, okay, that I have some CH scissoring, okay, a lot of other frequencies, okay. And then over here, 700, 750, okay, remember we were looking at my frequencies down here. Okay, here's the suspicion. I have an aromatic group, because you'll see strong frequencies here. If you take a look at that chart I gave you, you have very strong absorbances in the fingerprint region in this area for aromatics, out of plane bending. Also, I have a lot of carbon double bonded carbon stretches, and I have my CH stretches. So right now I'm thinking I have a ketone On one side of the ketone, I have an aromatic group because this is conjugated. On the other side, I don't know. Maybe I have more alkenes, but I definitely have some alkyl groups as well. So you have alkyl groups, aromatic, conjugated with a carbonyl. Okay, so what you're going to do for your IR assignment is you're going to write down your wave number. For the peaks, I put arrows on the ones I want you to assign, and you're going to give me an assignment. So, for example, if I put an arrow at a peak and it was 3050 wave numbers, your assignment, you'll just say sp2 carbon-hydrogen stretch. This means that you're most likely thinking that you've got an alkene carbon. If you see something like 1460, 1465, that's your sp3ch plane scissoring. So you'll see me put a bunch of arrows on the ones that I want you to assign. Okay, and I think I gave it to you in a PDF in a separate assignment, but here's your first one. You can see you have assigned these peaks here. Okay, oh, it's so pretty. And then this peak, these peaks. Okay, if you wanted to, I'm not requiring you to. You could assign there, but you don't have to. Okay, definitely assign these three. That should tell you a lot of what you have in there. Okay, this one, you just have 3 peaks that you need to assign. Okay. This one, look how broad that is. Okay, so you'll see these, I have 2 peaks here. I have this broad peak there. I have this here. I have those there. I have these guys here. Okay, got this peak, those guys there, and your last one.